Here we discuss about a project, a 0.4 volt nanovolt power high gain bulk driven two-stage OTA with self-cascode composite transistors and intrinsic current buffer Miller compensation. Here the ultra low power analog circuit plays a vital role in applications such as the Internet of Things, wearable electronics and biomedical monitoring systems and sensor interface, where the low energy consumptions with a compact area and reliable operations at reduced supply voltage are essential advantages of this work. Okay, so here, however, this systems also faces challenges such as a limited voltage headroom, reduced speed and performance degradations when operating in deep submicron technology. Here, the conventional gate driven OTA struggles to operate effectively below 0.5 volt, while existing block driven OTA, although suitable for low voltage operations, it suffers from low gain, high delay and poor robustness. The most reported solutions improve the gain or stability at the cost of increased power consumptions, large silicon area and additional biasing complexity, and also comparative studies across the advanced CMOS nodes are limited. To address these limitations, this work presents the design of a two-stage operational transconductance amplifications using a bulk driven technique with combined self-cascode composite transistors and intrinsic current buffer Miller compensation. This work implemented in both 45 nanometer and 22 nanometer CMOS technology, and this proposed architecture achieves a high voltage gain without additional bias voltage, while intrinsic current buffer compensated ensures the stable frequency response with a minimal area overhead. The novelty of this work lies in the systematic comparison of the proposed OTA across 45 nanometer and 22 nanometer technology, highlighting improvement in power consumption, silicon area and delay achieved through technology scaling while preserving stable operations. So this design performance is evaluated using a circuit level simulations on Tanner EDA platform, which key parameters such as a gain, power consumptions, area, delay and carefully analyzed. The results demonstrate that the proposed OTA achieves a ultra low power operations with improved efficiency and scalability. Okay, and making it well suitable for the next generation low power analog front-end applications. Now we can verify the paper. So this paper is fully designed for the OTA operations, which means a bulk driven two-stage OTA operations. Okay, OTA means here operational transconductance amplifier. Okay, so it's specifically used for voltage to current amplifications and critical for low power analog systems. Okay, so here it's a bias free operations. It will be supported for save power, area and improves robustness and integrations. Okay, so here they are designing a current buffer Miller compensation based architectures, and with support of 128 dB increases of gain without requiring an additional bias voltage. Okay, this work we developed a 45 nanometer and 22 nanometer CMOS technology, and prove the comparisons of these two architectures. So okay, so that is the advancement of this work. Okay, so this is a core architecture of figure 1. This architecture implemented with a two-stage bulk driven OTA optimized for ultra low voltage operation by systematically using 4 self-cascode composite transistor, which means a SCCT method, and intrinsic current buffer Miller compensation. Okay, the first stage is bulk driven true differential input pair. Okay, so which means M1A and M2A with SCCT devices, which allows us signal amplifications at low power voltage and avoiding gate override requirement, while the SCCT structure significantly increases output resistance and hence DC gain. A dedicated biasing network generates the internal bias voltage VB without requiring additional bias supplies, and making the design compact and power efficient. The second stage is common source amplifier with SCCT device and the stability is ensured using an intrinsic current buffer Miller compensation, where transistor based current buffering replaces a conventional amplifier and reducing compensation capacitance, power consumptions and area. Overall, this architecture achieves a high gain, low power and stable operations at ultra low voltage without extra bias support, making it well suitable for IoT, biomedical and energy harvesting applications. Okay, so this work we implemented in Tanner EDA tool. So this is the architecture. Okay, so here this is the OTA and TB OTA. Okay, so here we using only the two differential input analog signal, okay, and one output we will pick it. Okay, so without any threshold voltage or bias voltage we are not used in the circuit, and this circuit it will be operated at 0.4 volt. Okay, and offset it will be fixed with 0.2 volt input. Okay, so here it will be run with 22 nanometer CMOS technology. Okay, with additional spice commands we have analyzed the power and delay. Okay, so once we execute the circuit it will produce a waveform. Okay, here you can analyze it. So this is the input waveforms VN and VP. Okay, and this is the Vout architecture. So Vout architectures completely come with the more gain level. Okay, and this part and the comparisons we have analyzes in DSpice. Okay, so here this is a DSpice document. Okay, so here you can analyze the MOSFET and delay. Okay, so further the power consumptions we can analyze in the temp file, and we can analyze it here, the log file. It's having a MOSFET and nodes. Okay, so all the component features that will be available. Okay, and here you can analyze the power consumption. So power results will come with the average power consumption equal to 9.01148 e power minus 10. Okay, and this is a delay. Okay, so these features we have updated in a comparisons document. Okay, so here you can analyze the comparisons. So CMOS technology equal to 180 nanometer, that is the existing paper work, and this is the proposed work. Here we done 45 nanometer and 22 nanometer CMOS technology, and the MOSFET we measured with 20 in a paper work. Here we reduce the MOSFET count equal to 16. Okay, and power consumption also reduced, and area delay also reduced. Okay, and we also analyze the bias current, DC gain, voltage gain and output voltage range. Okay, we written an abstract document for this project. Okay, so title, base paper abstract, improvement and proposed title, proposed abstract, general notes. Okay, existing systems. Okay, disadvantages, advantages and related notes for this project. Okay, finally come up with literature survey and references. Okay, thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.
Introducing NXFE Innovation, your trusted partner in IP design and VLSI research. With over 300 plus completed projects in cutting-edge domains like low-power VLSI design, high-speed data transmission, signal processing, and secure networking, we offer tailored solutions for students and professionals in BE, BTech, ME, MTech, and PhD programs. At NXFE, you not only get expert-guided projects starting from RIS 6000 transparents, but also enjoy unmatched benefits like RIS 1000 to off on your second project, free documentation, and easy-to-understand video explanations. Plus, our rewarding referral program lets you earn up to RIS 2000 MANTs for every successful referral. Trust us to simplify your research journey with high-quality, affordable, and fully customized VLSI solutions. Visit our website to explore a comprehensive collection of projects, organized year by year from 2014 to 2024. The latest 2024 research projects are now available for publication, along with several 2024 non-completed titles, which are updated monthly with new possibilities. For application-based projects, interface designs, and mini projects, you can also rely on NXFE for top-quality solutions. We provide exceptional PhD assistance with full publication support and offer an installment payment option, allowing you to pay module by module. Let NXFE guide you through your research journey with flexibility and expert support. Thank you.